Hello, my name is Luke, and welcome to this PyTorch tutorial series. In this video, we're covering generative adversarial networks. So this is the first video in the series where we are looking now into generative modeling. We looked a little bit into generative modeling when we looked at VAEs. However, we covered VAEs in more of a representation learning context. But the next two videos, we're going to look at specific generative modeling algorithms. First one being GANs. So what is generative modeling? Well, up until now, we've covered mainly things like regression and classification. Pretty much divide everything up into one of those two categories, where we have some neural network that is learning to extract features from an input and predict some output, map that to some output distribution, either regress to a value or you've got some discrete distribution for classification. So even things like the object detection and the autoencoders, they're all kind of regression or classification potentially tasks. So those tasks involve extracting features from the input so that you can predict some output target. With generative modeling, however, what we're doing instead is we're trying to train a model that can, instead of learn to identify and extract features, that it learns to produce those features within a given data set. So, as I said, with a VAE, we saw how we could regularize the latent space of a autoencoder with the KL divergence penalty, and saw how we could try and smooth it out and regularize it, or try to get it to fit the prior distribution. And then that helps regularize the distribution, but also we can try and sample from that bottleneck of that distribution to try and produce new values. And we saw how it kind of works if you regularize it heavily, increase the penalty quite a bit. But we also saw that we lost a lot of information when we did the reconstruction because we're forcing sort of all the inputs to have the same similar distribution. And so the quality of the outputs wasn't that great. They were blurry images. So we kind of lost some information. Now, there has been work done for VAEs where you have different types of loss functions. So we used a mean squared error. So we used a regression expectation over all the pixels. Tried to reduce the loss in that case, but you can have additional loss functions that try to preserve some of the higher frequency components, similarity losses, perceptual losses, those sorts of things. Well, in those cases, what we're trying to do is we're trying to encourage the VAE to produce some higher frequency components that, like the mean squared error, won't encourage it to do or prioritize. But even in those cases, the quality isn't so good. What we really want is some sort of loss function or objective that sort of tells the decoder of our VAE, yeah, I know some of this high frequency component information has been lost through the random sampling, but sort of just produce whatever would still fit that distribution, right? What the decoder is producing is the expectation over all the possibilities. What we really want it to do is produce one potential possibility for that latent embedding. So that's something similar to what we're doing with our GANs, with our generative adversarial networks, except our generator doesn't have the encoder there. So there's a lot of ways you can think about what a generative adversarial network is doing. So there's a lot of analogies that get thrown around. You know, you have your artist and your art critic. You have your artist producing artwork that's trying to fool the art critic, and the art critic is trying to learn to discriminate between real art and this fake forged art. However, I don't really like that analogy too much. So I know we're going to focus on thinking about the discriminator, thinking about the training process for our GAN as some generator that is trying to map from one distribution to another. And we have another model that is trying to, or is basically saying whether or not this sample comes from a true distribution or a fake distribution, or true distribution or some other distribution. So in general, at a high level, this diagram here shows the training process of our GAN. We call it an adversarial training procedure because the two networks that we use in a GAN, our generator and our discriminator, have sort of competing objectives. They don't have the same objective. So the generator is like our decoder in our autoencoder. At this time, we're just giving it a purely random noise sample as the input. So we can think of this as mapping from two different distribution spaces. So we give it a sample from a standard Gaussian distribution, and we want it to map from that distribution to we sample from the distribution of our data. So we can think of all the images within our data set as coming from some complicated data distribution, some very complicated data distribution with a lot of structure in it. And we want to map from a very simple distribution that we can easily sample, standard Gaussian distribution, and map from that distribution to a sample from our data distribution. Right, so how do we get our generator to actually do that? Well, we need a second network, and our discriminator we can think of as a loss function, but this loss function, this equation, is a neural network that we also train. And the discriminator is trying to determine whether or not the input sample comes from the data distribution that our data set fits to, or some other distribution. You often see it said that the discriminator tries to classify between real and fake data, your forged art or your real art. The discriminator doesn't really do that. Specifically, it's trying to tell whether or not the input comes from the data distribution or some other distribution. What I mean by that is if we, for example, trained on a data set of dogs, then once the discriminator is sort of trained, if I were to give it an image of maybe myself or, I don't know, a car, technically the discriminator would say that that image is fake, or that image does not actually come from the real data distribution, even though that image is a real image of a car or of a person or whatever. Not really real or fake images. It's does this image come from the distribution underlying the data set images or not? Right, so how do we train the discriminator? Well, we have samples from our true distribution, but we need samples from theoretically every other possible distribution, right? Or some samples from a different distribution. That different distribution is our generator in this case. So you can see the sort of adversarial or competing objectives here. The discriminator is basically trying to say, does this image, in the simple case that we're going to look at today, does this image come from true data distribution or does it come from some other distribution? Our generator is trying to map samples from some simple distribution to a data distribution, but at the start it's not going to be quite there yet. And so the generator is being trained from the discriminator. The generator produces an image. We then pass that through the discriminator and we try to get the discriminator to output that as a yes, this image does come from the dataset distribution. We then backpropagate through the discriminator like we would a normal loss function into the generator and update only the generator. And then of course the discriminator trains separately, trying to correctly classify the generator's image as not coming from the dataset distribution and the real images as yes, coming from the dataset distribution. So it's an unsupervised learning method here. Okay, so hopefully that high level explanation makes some sense. So we're going to be using the MNIST dataset again today. We'll go over the hyperparameters a bit later on, but note that we're using quite a large batch size, but we'll get back to why in a moment. So we're going to be implementing a DC GAN, deep convolutional GAN. Networks won't be too deep, but technically they are deep neural networks and they're convolutional neural networks. So our generator will be like a decoder of an autoencoder, and our discriminator will be structured like a classifier, basically. There's a few differences between maybe a classifier and a decoder and the actual networks that we're going to be using for our generator and discriminator. The main one you'll notice is that our models tend to be quite a lot larger and wider than, say, a classifier or even just a decoder of an autoencoder. That's because, unlike, say, classification and regression, where we only need enough model capacity, enough kernels in our convolutional layers so that it can extract enough features from the image to do classification or regression, extract enough information for classification to determine what class it is. With generative modeling, however, we need to be able to capture and extract all of the possible information in our dataset distribution. We need to be able to capture it all and replicate it all. So both our generator and our discriminator are going to be quite larger than sort of an equivalent network for some other objective. That's a main thing, and that holds true really with all sorts of generative modeling techniques. Networks tend to be quite a lot larger. They're not going to overfit because they need to actually retain and model quite a lot of information. So our generator is going to be quite a lot larger because it needs to produce or hold and replicate a lot of features, and our discriminator is going to be bigger because it needs to not just extract enough features to determine between a cat and a dog, but it needs to be able to identify all the information within an image of, say, a dog, or MNIST in our case. Okay. But apart from that, really, the generator network here that we can see is pretty similar to, say, our decoder network. I've made it pretty straightforward in our case here. The input to the generator, as I mentioned, is going to be a 1D vector of random Gaussian noise, and I'm using a conv transpose to upsample that. So the input shape is going to be latent size by 1 by 1. So it's a 1 by 1 feature map. I don't need to use a conv transpose here to upsample it, but I'm upsampling to a 4 by 4 feature map. And then I'm just using convolutions, 3 by 3 kernel, 1 stride, 1 padding, and I'm using nearest neighbor upsampling to upsample it, which we've seen before. And then of course we just go conv activation. I'm using LU activation here. I'll get to Y in a moment. Then conv batch norm activation, and then our nearest neighbor upsampling. So upsampling to a 32 by 32. A transform here, I am resizing the 28 by 28 MNIST to 32 by 32. So it's a power of 2. It's just easier to handle with our networks. Okay, going on to our discriminator network. Again, pretty similar to a standard classification network, but it is a bit wider than I would probably make an MNIST classifier, because as I mentioned, model a lot more information. But again, conv activation. Note, I'm not using batch normalization here on every layer. I'm just doing it once at the end. I'll get to Y a bit later on. And I've also got a dropout layer here to prevent it from overfitting it. Okay. So what is the actual training loss or objectives that we're going to be optimizing here? In our case, we're going to keep it pretty simple. We're just going to treat our, we're going to use the Shannon-Jensen objective. We're basically going to do binary cross entropy loss, right? So we're going to treat the discriminator's output as just a probability of coming from the true distribution. The output of our discriminator here is a single value. I'm using comms all the way down. I'm not using a fully connected layer, but I am just reshaping. The last convolutional layer has one channel output, and it'll be a 1 by 1 by 1, so just one value, and I'm just reshaping it here to be a batch size by 1. Got to point that out. So just a 1 value per input. And that's going to be, right, probability of it coming from the true or some other distribution. So as I mentioned, how we train this, we randomly sample. We can either train the generator or discriminator first. I think I'm training the discriminator first, if I remember, generator first. So what we do is we sample our random Gaussian distribution, put it through our generator, and then we pass that fake image to our discriminator, and we want to maximize the output. Basically, we want to get our discriminator to classify that as a coming from the true distribution. So for our binary cross entropy loss, our target will be 1. So I've got a function here that returns the binary cross entropy loss. Basically, we put the output of the discriminator in, and we say, should we try to get the discriminator to classify this as a 1 or as a 0? So for our generator training, this should be true, and we'll get our binary cross entropy with our output and our target as 1s, right? For our discriminator, it will be false for the generated images and true for the real images here. I'll just put it in a function just to make it a bit cleaner in our training loop. Get to the other loss function later on. That's really the objective again. And then we train our discriminator. We take a real image or a generated image and then classify them with the true labels: real, 1, fake, or not real, or coming from a different distribution as 0. Okay, so we need to initialize each of our networks. Each will have its own optimizer. We don't want the same optimizer because they are competing objectives. All right, and when we backpropagate through the discriminator to train the generator, we don't want to be updating the discriminator's parameters at all. Okay, so a latent noise dimension, that's the channels for our input. For our generator, it's 128, width 32, with multiplier. I'm going to create a fixed latent noise sample, so we're just going to sample a vector of latent noise, and what we're going to do is every epoch, we're going to pass this to our generator and make a little animation like this one here, which I'll talk about now. So this is basically the output of our generator given the same input noise vector over training. So you can see it started off with a really random looking image, and we're slowly converging to some nice MNIST images, a little bit of wobbling here. You can maybe drop the learning rate. Okay, where are we now? Create an optimizer for each of them. Skip this for now. Just make some loggers for some losses, whatnot. Okay, so I've spoken all about GANs and how we train them, what they are, what they're aiming to do. However, there's a lot of problems with training GANs. They are pretty unstable. There's a lot of different ways that they can collapse. We haven't really seen a lot of unstable training up until now. Maybe if you had your learning rate too high, might explode your gradients or something like that. But generally, we get a nice steady convergence of our loss. But we'll see in this lab or this notebook, the loss function doesn't really converge nicely. It kind of goes all over the place. I don't think anything we've covered so far really similar to that. Right, we did stochastic gradient descent. We got a bit noisy, but as we'll see in a moment, it can get a lot noisier. So let's look at some of the failure cases, problem cases with GANs. So there's been a lot of work in the literature. You can look at the formalization of the training procedure of a GAN as a min-max game, where the generator is trying to maximize the output for its generated images and the discriminator is trying to minimize it. The simplification. And in that competing objective, there is a lot of room for instability. So here's some common failure points here I've noted. At the beginning, the distribution and real and fake are far away from each other. It can be easy for the discriminator to tell real from fake. So this is a lot more of a problem with what I find with high resolution images. You're trying to train larger models with a lot of generative modeling methods. As you scale the size of your images up that you're trying to generate, issues scale sort of exponentially, or it becomes exponentially harder to train. Like diffusion modeling might not be as bad, but especially with GANs, scaled quite a lot. So if the images produced by the generator are really far away from images from the real distribution, your discriminator can pretty quickly learn to tell the difference. And that sort of leads into the second point. If the discriminator becomes too good, it can stop producing useful gradients to the generator. So basically, the discriminator has pretty much worked out exactly what is real and what is fake, using features of the generated images that the generator potentially can't easily change too much, and basically the generator gets stuck and can't get any better. So it hasn't actually yet learned to produce images from a real distribution, but it's still converged and still becomes stuck. Conversely, the discriminator can actually become bad, or the discriminator might not train quickly enough and can't tell the difference between the real and fake samples, and the generator basically is able to produce any sort of image, and the discriminator maybe doesn't have enough model capacity, maybe its training procedure is done incorrectly, can't tell the difference between real and fake samples, and the generator gets a really, really low loss, but it's still not actually producing good quality images, right? This is a consequence of the loss function of our generator being learnt. It's not fixed during training. We have this alternating training procedure, so our loss function is changing over time for our generator. Right. Point 4, the generator overpowers the discriminator, and the discriminator cannot tell real from fake, so the generator just learns and becomes good. That's similar to point 3 as well. And then the final point here is the generator starts outputting only a few images, so we get mode collapse. So technically our discriminator is just trying to say, is this input from the true or some other distribution? If our generator just produces the same image that is from the true distribution over and over and over again, there's no real way for our discriminator to sort of tell the difference between, the generator producing lots of diversity and producing only the one image. However, there are some ways you can combat this last point here, and we're actually implementing one of them, which is just to use batch normalization in our discriminator. If all of the generated images are the same or very similar, and deviation or the variance of the features over the batch is going to be quite small, dividing a number by a small number, we can potentially get some spikes and peaks in this activations here, and the discriminator can detect those. However, I've only got one batch normalization here because turns out that batch normalization actually helps the discriminator a lot. And if you put a lot of batch normalization in the discriminator, it can tell too quickly and overpower the generator a bit too quickly at the start and doesn't let the generator sort of warm up and start learning before it sort of converges, which is we've already mentioned here. Just one batch normalization layer near the end seems to be good enough. And I've also got a lot of batch normalization in the generator, which again helps it produce a lot of diversity, or work out it's not potentially producing a lot of diversity. There's some other points here that I haven't really mentioned, or ways that the discriminator can become too good. You've seen some that you might not expect, right? The images from the real distribution or our real images are all usually 8-bit images, and so the actual values the input can take come in discrete steps, whereas the output of our generator is continuous. The discriminator could potentially tell the difference between a discrete input and a continuous input, even though it's not really looking at all of the actual the image as a whole, whether or not the image looks good or similar to the actual real distribution. It's looking at whether or not pixel values come in discrete steps or not. So you can add noise to your input. A little bit of noise can help with that. Again, because we're training the discriminator while we're training the generator, we're learning the generator's loss function as it trains, and so it's always changing. The discriminator can have sudden changes to its parameters or sudden changes to that sort of optimization space that we're training the generator in, and that can cause big changes to the generator's parameters, right? So the objective of the discriminator might be descending nicely and suddenly it just drops, and we get a huge spike in the loss for our generator. The training can kind of explode. For example, maybe your generator's sort of learning, and maybe it's producing some weird features that the discriminator's learned to detect, saying, no, that's not from the real distribution. And then suddenly the generator learns to stop producing those features. Well, if the discriminator has been focusing solely on those features and the sort of loss for the discriminator has gone right down, if the generator suddenly stops producing them, or relatively quickly stops producing them, then the loss from the discriminator can spike. We can spike that loss and update the discriminator and exploit our parameters, and that can go into the generator as well, and the whole thing will just collapse. So there's lots of potential issues, and there's been a lot of work around this as well. Training with a large batch size as well helps with the mode collapse issue, and just helps as well reduce the noise in the gradient updates as well, because there's already enough noise in our system. But so a large batch like a 512 tends to help. There's been works like Big GAN, which shows that the larger your batch, the better quality your images are. Really kind of a one-to-one, converges eventually, but pretty good rule. So let's look at the training loop. As I said, we're training the generator first. So we do one step of gradient descent for our generator. So we randomly sample from a normal distribution, and we pass that noise into our generator and get the generated output. Pass that batch of generated outputs into our discriminator, we get the output, and then we calculate our binary cross entropy loss with a true or real labels of ones, and we backpropagate that through the discriminator and into the generator, and we only take a step for the generator's loss function. So we're only updating the generator here. I'm just going to append the loss as well, keep track of the generator loss. And we do a similar thing with the discriminator. We pass the real images through the discriminator, and we pass fake images in, and then we train with true for the real images and false for the fake images. Note here, I'm passing the real and fake images in different mini batches. This again can help with the discriminator learning the difference between the real and fake, and also with the mode collapse. Because if I pass only the fake images together at a time, then we can more easily see that all these images have collapsed to the same image or a similar image. Well, the features aren't very diverse. So by doing this forward pass in 2 different steps, we're able to give our discriminator a bit more information about batch of information. So now we're kind of doing a batch classification rather than an individual image. And I'm averaging the losses together as well to train the discriminator. It's kind of just scaling down the discriminator so it doesn't get too good. Again, I've sort of tuned this so it works, but there's also little quirks. You can play around with the hyperparameters and the code specifically to try and get it better or worse. Finally, the last thing we do, every epoch, I'm just, as I mentioned, putting the network, the generator in eval mode, passing that fixed latent vector of noise and getting our test images. And we're just putting that into a grid, make grid, and then converting that to a NumPy 8-bit image, integer image, and appending that back in training mode. And then once we've trained, we can save that as a GIF. You can save your own little GIF. So as you can see, I've already trained GAN for 100 epochs. So it took a bit of time, probably took around 20 minutes to train, depending on your setup. So you can see the objectives for our discriminator at the top and the generator at the bottom. And you can see it's very, very noisy. There's no nice sort of convergence here. You can see generator kind of drops at the start and then discriminator increases, but then discriminator sort of works it out and the generator gets worse. Interestingly, as the discriminator gets better, the actual generated image quality improves, even though this is the generator. So the discriminator needs to learn how to tell the difference between real or the images from the distribution and other distributions. Right? It needs to actually be able to tell the difference between those to provide feedback or to provide useful feedback to the generator. So this is why we have this min-max competition, but we also don't want one of the networks running away from the other, because we want the discriminator to get really, really good so that the generator has the information to generate real images, because the generator never actually sees any real images. That's the interesting thing. All of the feedback it gets is from the discriminator. It's the discriminator that learns to produce this cloth landscape that the generator can learn from. Right. So it's interesting. Right. So the discriminator, maybe if we keep training, it'll get better and better. Maybe the generator loss will converge down again. But in any case, you can see we've got reasonable images here. I think I did train a bit longer to get these nicer ones here, so you can train it for a bit longer as well. So the last thing I'm going to cover is, as I mentioned, there's a lot of different variety of GAN loss functions, training procedures, architectures to improve bit by bit all the sort of quirks of a GAN. A lot of the attention these days has moved to other generative techniques. GANs still are pretty good in that you only need to do a single forward pass of your generator, which is compared to, say, the diffusion models, quite a bit smaller, and still allows you to have some control of the actual generated images. But yeah, as I mentioned, a bit unstable to train. So one other sort of thing I've implemented here is the Wasserstein GAN, and that basically, in that paper, we changed the loss function. So instead of using this binary cross entropy and Channing-Jensen objective, Wasserstein loss, and this is a pretty simple objective really. All we're doing here is trying to increase or decrease the output of the discriminator, whether or not the image is from the true distribution or some other distribution. So you can see the real label, we're going to minimize the negative of the output. So we're going to maximize the output of the discriminator. For the fake label, we're going to minimize. So basically, we're trying to get the discriminator to push the two outputs further and further apart from each other. Right. And that's a bit nicer than the Channing-Jensen, again, because we've got this sort of sigmoid at the output of our discriminator. As the discriminator is sort of converging to outputting a 1 after the sigmoid, that means that the output value has to get quite large, or very, very large. And as I mentioned, if, say, there's some small change in the actual generated images and the discriminator is no longer able to classify, then the output of the discriminators are large in one direction, and then it suddenly, the label is incorrect, and it kind of just explodes. So having this linear output of a discriminator pushing it one way or the other can prevent instabilities. However, you can get a runaway where the output of the discriminator becomes really, really, really large, because we're just saying maximize the output and minimize the output. So what we typically do as well to regularize the discriminator network usually is, firstly, we're going to initialize it with a smaller parameter values so that during training we can actually restrict restrict the magnitude of the parameters of the discriminator. You can do generator, but really you only need to do the discriminator, so that just prevents the outputs exploding the discriminator. We just basically just clip it every iteration. Doing at the start of every iteration, we're just clipping the values of the parameters of our discriminator between some range. Later methods use something called a spectral normalization, which is just, again, a regularization of the parameters, stop them exploding, right? And there are other losses like a hinge loss as well, which is pretty similar to the Wasserstein loss. Well, I'm not going to run this here, but feel free to use that. I wouldn't clip the generated parameters, just clip the discriminator parameters, and don't forget to initialize them to be quite small, because if you don't initialize them to be quite small values, you'll get pretty much all of your values being clipped to this value or this value, and so you won't get a nice distribution of values. You'll only get, it tends not to work as well. Okay, so have a play around. Getting familiar with the behavior of a GAN, useful in knowing how to actually structure and tune your hyperparameters. It does take quite a bit of fiddling around with, and every time you run the training procedure, you tend to get a bit of a different result. Fortunately, it's not quite predictable as some other generative modeling techniques, but as I said, once you've got the network, you can generate as many images as you like. So I'll leave the video here. I'll catch you in the next one. So we're going to look at, as I said, diffusion models in the next one, a bit of a different training procedure. If you like that video, I'll leave a comment, leave a like, and subscribe. Let me know if you have any questions or any ideas for future videos, but I'll catch you in the next one.